The first order of business is we have an exam coming up a week from today on Wednesday. So maybe I should pull this over just for a second and then put the visual I have up here again. On Wednesday, 4/21, by email again. I don't think COVID's gone enough so we can do this in class. Don't come to class. We have exam 3, our last midterm. It's going to cover, let's see, sections 10-8 that we didn't get to do in the last test on Taylor and Maclaurin series. Very important section. And then 11.1 to 11.5, chapter 11. All right. We'll finish that today. So you'll have a week to prepare. The practice exam will be on Canvas in a couple of hours, probably actually about an hour and a half after class. Okay, I don't guarantee all problems will be off the practice exam. All the problems will be similar to homework. I put a good smattering of homework on here, things I think are more important, so most of the exam will be similar to practice problems. This should be an easier exam than the other ones, I think. It's not as deep, except maybe the first section is kind of hard. But come see me in office hours, ask me lots of questions, and on Monday we'll review for the test. So if you looked at this by Monday, you got 5 days to look at it, then we can go over some of the questions you have. Any other comments on the test? It'll be just like before, open book, open notes. Just no person can help you. Okay? Yeah. Online by email, just like before. Okay. So here's just for fun, if you want to see a nice blurb on these things, Wikipedia often has a lot of these things. People in higher education often write pretty neat articles that sort of summarize compactly topics. I just Googled Wikipedia Conic section, if you watched me on the screen there, and clicked on the first link. And it goes through all sorts of history of conic sections. It's really neat. They got pictures of ancient documents, not ancient, old documents. But it goes back to ancient Greece, and they talk about Apollonius and so forth. And here's, well, I guess I better get this off to go fix it. Hold on. Here's a nice picture of orbital mechanics, right? If you put the sun at the focus of each conic section, you can have a planetary orbit so the circle of it has just the right energy. It will go around in a perfect circle. I mean, nothing's perfect like that because the sun isn't a perfect. Newton showed that a sphere acts gravitationally as though all its mass is concentrated at its central point. Now, the sun isn't a perfect sphere, but it's pretty close, right? And so it's not perfect inverse square law that Newton estimated, but it's real close. And so a planet can go real close to a circular orbit, ignoring actually relativity. Einstein showed that Mercury is close enough to the sun that its orbit is kind of perturbed a little bit. So all the planets orbit, however, in elliptical orbits, approximately again, pretty close, because the sun is almost a point, can almost be treated as a point source of gravity. And so you'll find all the planets travel in elliptical orbits. This was Kepler's great discovery, right? He got Tycho Brahe's exhaustive observations and went through all of them, and he was all about looking for God in the heavens and so forth, all these beautiful things. Some of these things are pretty fanciful and speculative, but he did find this. He found out planets go in these nice elliptical orbits, real simple equations like we saw last time, right? And with the sun at one focus, and there's other neat laws like it sweeps out equal areas of the ellipse in equal times. It's sort of clockwork of the heavens kind of thing. And so all the planets are doing that pretty nearly. And I started to talk about Mercury. Einstein showed that if you take into account relativity, actually the ellipse that Mercury goes on gradually tilts, and it moves around like that because of relativistic effects on top of our standard gravity model. And then if you just have escape velocity as a parabola, a little more energy, and it has with escape velocity a hyperbolic trajectory. And so all those things come up in planetary observations, for instance. Thought you'd just like to see a few applications. All right, without going through everything again, here's some of the things. Like here's you can go into more detail. Here's our major axis here and our minor axis, and here's the foci of the ellipse and all that sort of thing. And it goes through some of the optical properties and so forth. Talks about some of these things we did last time, whispering galleries and so forth. So I'll just leave that there and say there's some interesting stuff online you may want to look at just for fun to supplement your education. And we'll talk about the equations of these things today some more. We did quite a lot of them last time. Uh-oh. And we got up to the hyperbola, and we said, from that definition of hyperbola, that it's the set of all points such that the difference of the distance from two given points called foci is a constant. If you put it centered at 0, it gets an equation always like this: x squared over a, well, let's write it the way the book does, x over a squared minus y over b squared equals 1. Looks just like the ellipse equation, but minus instead of plus, so it's easy to memorize all these things too, right? This was the standard equation for hyperbola. And we said this is for a hyperbola that's centered at the origin with foci along the x-axis. The positive terms tells you what axis the foci are along. Unlike the ellipse, the bigger number a, or the bigger number a, in ellipse a is always bigger than b. Maybe I should remind you, it's been a while, right? So this was the ellipse equation. I guess I usually wrote it like this in the book. This was the standard equation for the ellipse. A is always considered to be the bigger number. It's the semi-major axis length, half the axis, the longer axis length. But you always treat A as bigger than B, so if you want the foci along the y-axis, you put A under y and B under x. Now the foci go vertically. That's what we said. It's different when the hyperbola, the equation only changes by a minus sign, but the result, to get the foci on the y-axis, what you do is you interchange x and y in the equation, and that's equivalently interchanging the axes. And so for foci along the y-axis, you put y over b squared minus x over a squared equals 1. That's a hyperbola with foci along the y-axis. At 0 plus or minus c. But this one here will have foci along the x-axis at plus or minus c0. How do you find c? Remember that one? We wrote it right at the end. It's the Pythagorean theorem. C squared equals a squared plus b squared, which again is a little different from the ellipse. The ellipse had an equation like this, and then if you interchange x and y, so it looks like this, equivalently interchange a and b, then that interchanged the foci, but you kept a bigger than b. But this one always satisfied, in any case, a squared equals b squared plus c squared, the relationship between a, b in the equation, and c, the focal distance. For the hyperbola, you put a minus instead of a plus. Whichever term is positive has the focal axis, not the one with the bigger number underneath. And then it's the regular Pythagorean theorem, c squared equals a squared plus b squared. C is the biggest number on the hyperbola. A is the biggest number on the ellipse. You can kind of see this if you sketch it. Right? We started to sketch this. There's a focus at minus c0 and a focus at plus c0. Now the distance from here to a point on a hyperbola subtracted from the distance from here to a point on a hyperbola has to equal a given number, which means that the hyperbola goes something like this. And this point is the vertex. We call that point A0. Why do we call it A0? If you plug in y equals 0 here, you find that the x-intercepts are x equals plus or minus a. So the points on of intersection with the x-axis are minus A0, A0 just from the equation. And then C has to be bigger so that this difference is a constant. Right? You're taking this one minus this one. And that's the same as the difference, this distance minus this one is the same as the difference, this one minus this one. And so there's two branches then. There's this branch over here that looks just like this one flipped over. And that is the standard hyperbola. You put the center at the origin, foci at plus or minus c, has an equation of this form that satisfies c squared equals, of this form, that satisfies c squared equals a squared plus b squared. Does that sound familiar, plus a little more stuff? That's how you deal with foci. Now we can figure out how to graph foci, or graph hyperbolas, and from a graph figure out what the equation is, or from some of its characteristics like the foci and vertices, figure out what the equation is. All right, so I'm going to get rid of this stuff because we don't need this yet. But the idea is in any graph, if you interchange x and y, it's equivalently interchanging the axes, and so it flips it from opening horizontally to open vertically just by interchanging x and y. And so that's what's going on there. And then also in all these conic sections, you can translate them, and we'll discuss that again too. Remember also that the hyperbola turned out, and the calculus shows this, sometimes you get too many details, it gets to be too much, but we can show without too much difficulty that actually these curves approach asymptotes. We didn't get to say this yesterday. The asymptotes go through the origin, and they have equations when it's in standard position like this. Y equals plus or minus b over ax. You can see how to do this, right? How to find these asymptotes. If you add this word over here, this term over here, and subtract the one over there, then take the square root, solve for y as a function of x. If you take the limit, you'll find out that y looks like b over ax plus or minus. Anyways, you just solve for y in here and take the limit to figure out these asymptotes. But there is the hyperbola that we want to consider. And it has nice optical properties too. For instance, if you put a light source at this focus, right, and shine it, forget this branch, shine it onto this surface here, it's going to go out at an angle that makes it look like it's coming from this focus. Same thing here. So if you want to create an optical illusion, you can put your object here, and somebody looking over this way will think it's sitting here. Right? So all these things have neat optical properties. We talked about the ellipse, how it can focus light from take light from one focus and bounce it off the ellipse to refocus at the other focus. You can create a false image in the ellipse by putting a light bulb at one focus. It'll look like it's at the other focus. And you've got this kind of optical illusion here. So it's kind of amazing that these things so simple would have all these interesting optical properties, but in fact they do. All right, I'm going to erase all the picture here then. Put the equation for the asymptotes back up. Now what I want you to be able to do is put these things elsewhere on the plane, figure out equations for these things, and sketch them. So suppose I said, let's now sketch. Oops. I've been finding these don't show up very well online. I'm starting to have to just write in black, I think. You learn as you go here. Just about the time I get this right, we'll be done with all this stuff, and I won't need it anymore. That's Murphy's Law, right? So suppose I wanted you to sketch whatever this is, whatever conic section it is. What is it? Y minus 2 over 5 squared minus x plus 1 over 12 squared equals 1. What does that look like? Yeah, you're right. Good. One of the things I want you to get out of this is to recognize from the standard equations how to recognize when somebody's giving you one of these conic sections. They come up a lot in practice, as you've seen. Here's what we're doing here. We think of, without this minus 2 and plus 1, we would have y over 5 squared minus x over 12 squared equals 1. And notice that a is not bigger than b here. The hyperbolas do not have the restriction that a has to be bigger than b like the ellipse did. Right? And now that's the, if I saw this one, I'd say, oh, that's this form. That's a hyperbola with foci along the y-axis because y is first, right? Hyperbola with vertical foci. Now, how do I sketch it? Well, if I'm sketching this one, not quite this one yet. Then I'll carefully sketch this here. So, well, this one is centered at the origin, right? Because it's the standard form with foci along the y-axis. Where are the foci? Well, c squared equals a squared plus b squared is 5 squared plus 12 squared, right? C squared equals a squared plus b squared. And so c is the square root thereof, which comes out to be 13, right? If you work it out. Which means I can go up to 0, 13, and down to 0 minus 13. Remember, the foci are vertical on this one instead of horizontal, but I draw the same picture, just opening up and down when y is first. Now, what is A? A is 5, so the vertices are actually 5 units out. So it's in here somewhere, 0, 5, and 0, minus 5. Those are the vertices. If I really want a good picture, I want to plot the asymptotes. Y equals plus or minus b over ax. Well, b is 12, and a, oops, you know what? I'm sorry I put this backwards. B on the hyperbola, b always goes under y, and a goes under x, and that way it's y equals plus or minus b over ax regardless of which orientation you have. So this is y equals plus or minus b over a is 5 over 12 x. So I can sketch those asymptotes. Maybe I can get away with putting those in blue, huh? Hopefully show up. And so I sketch this, lines of slope 5/12 through the origin, right? This one is y equals 5/12 x. This one is y equals minus 5/12 x. Now I know how to draw it exactly, right? I draw the hyperbola through the vertices approaching the asymptotes, going up and down. So one approaches this one like this, and the other approaches the other asymptotes like that. Nice picture of the hyperbola just from the asymptotes and the vertices, right? And then the foci are kind of nice. I might ask you to sketch those in the exam. If you look on the practice exam, I did something that you didn't have on your homework. I said sketch some of these because I want you to do that. They should say that in the book, but they can't do that online. So some sections they just say identify the sketch. But I think it was hard in this section, so they just didn't do it. So I'm asking you to do a few sketches. You got to wait to learn how to sketch like this, right? Any questions on that one? I've got sort of a helping tool to apply here. Every conic section book does this. You know how you can draw these asymptotes really accurately? If you want y to have, you want the slope to be 5/12, what you can do is go up 5 in y and over 12 in x. Go up to 5 where the vertex is, and over 12 here, and then down 5 and over 12, and make a rectangle. And if you make a 10 by 24 rectangle like that, the foci will go right through the corners, if I drew it right. Apparently I didn't. But so you can draw A up, B up here, and B down here, A over here, and A over here. Draw a rectangular box, and the foci go through the vertices of the box. Then you make accurate asymptotes. I shouldn't say foci. The asymptotes go through the corners of the box. Now, wait a minute. That wasn't the problem. I was doing this one. How do I fix it? When you replace in any equation on the plane, x by x minus a number and y by y minus number, it's just a translation. It's exactly the same shape, like this a rigid figure. You just slide it over on the plane. If y is 2 units greater and x is 1 unit less, you'll square the same numbers here that you did here and still satisfy the equation. So the numbers satisfying this are just the numbers satisfying this with y 2 units more and x 1 unit less. It's whatever you subtract here. So all I've got to do is move it so the center is at 2, -1. You just read that off of here, whatever's subtracted. Maybe I better draw this in black just in case. I think blue shows, red doesn't. I don't know. Center, 2, -1. Right? And so if I just make this point 2, -1, then I just got to put the axes about here. I put two dotted lines there through the center. Oops. Maybe that's a little too far. 2. Okay, so that makes the center about 2, -1, right? And now I've got it. And the equations of the asymptotes change too, right? Y equals minus 5/12 x. How do I fix that? I just translate the asymptotes, right? So I'll get rid of the blue here. It was y equals minus 5/12 x, right? All I do is replace x by x plus 1 and y by y minus 2, and that translates the asymptotes too. Here's this asymptote. Y minus 2 is minus 5/12 x plus 1. And this asymptote, similarly, just replacing y by y minus 2 and x by x plus 1, I get y minus 2 equals minus 5/12 plus 5/12 x plus 1. There we go. There's my new asymptotes. That's how you can sketch a hyperbola. When you see an equation like this, recognize it's just a translation. Replace y by y minus 2, x by x plus 1 from a standard equation for a hyperbola. If y comes first, the hyperbola opens up and down. If x comes first, the non-negative term, it opens left and right. You can calculate the foci from A and B, right? That's all there is to that. All right, so now we want to do some similar problems. Uh-oh. Suppose I gave you this. Uh-oh. Not getting enough sound. There we go. It's a little better. This time we'll say find the equation of the hyperbola, or just find the hyperbola that has these properties. Suppose the asymptotes are y equals plus or minus x, and the vertices are plus or minus 4, 0. What can you do? Well, first, the vertices tell you the center. I always say go get the center first. The center is halfway between these 2 points, so it's at 0, 0. You just average the x-coordinates, 4 plus minus 4 over 2, average the y-coordinates, 0 plus 0 over 2, and you find out the center is 0, 0, halfway between the vertices. Now, what does this tell you? Y equals plus or minus b over a. X is always the asymptotes, so b over a must be 1. Which implies that b equals a. So I got center 0, 0, 0, a equals b. What else do I know? Remember, the vertices are a units from the center. So this must be a. Right? From 0, 0, the center, to either one of these points is 4 units. A equals 4, distance center to vertex. So a equals 4 and b equals 4 is what I've deduced. Does it open left, right, or up, down? Yeah, it's left, right because the vertices are horizontal, right? So a equals 4 horizontal vertices. So we're just going to the standard equation. We want to write x over a squared minus y over b squared equals 1 is a hyperbola at the orbit with center at the origin and horizontal vertices. X term first for horizontal. Which means we have x over 4 squared minus y over 4 squared equals 1 is the equation for this thing. How about that? So that's the idea. They'll give you a couple ideas, a couple things like the vertices or the asymptotes or the foci or something like that, and you'll be able to figure out the other letters using the equation. Now, suppose I ask you for the foci. What are the foci? Maybe where are the foci? How about that? All right, for the hyperbola, c squared equals a squared plus b squared. So you write c is square root a squared plus b squared is square root 4 squared plus 4 squared is 4 square root 2. So the foci, since it's centered 0, 0 and horizontal vertices, it's also horizontal foci. It's plus or minus 4 square root 2, 0 are the 2 points where the foci are at. Put 3 dots. 3 dots mean therefore in mathematics. So therefore, those are the foci. Okay? Now there's another one, right? We did circles, ellipses, hyperbola. We still have to do parabolas. These have a similar definition. These are all points x, y, whose distance from a given point, called the focus, is equal to the distance to a given line not containing the point, called the directrix. By the way, the ellipse and these other ones also have directrices, but okay, from a given focus to a given line not containing the focus, called the directrix. And once again, you get a pretty easy equation if you just put it in the right place. The standard equation, I guess I should draw the picture here before I draw the standard equation. Here's the idea. Suppose I put the parabola, so the way you're familiar from algebra is the vertex is it sitting at the origin. And I put this focus here at 0C. All right, so its focal length apparently is C. And then the directrix has to be down here at y equals minus C. Can you see why? The parabola is defined to be the set of all points that are equidistant from this point here and this line here. So this point here, if I go straight down C units to the vertex, we'll call this the vertex now. Halfway between the point and the line, right? There's a perpendicular always from the point to the line by Euclidean geometry. Halfway there has to be what we'll call the vertex. And then this has to be the other half distance, also has to be C. So if this is 0C, then this is y equals minus C for the directrix. So there's the focus at 0C and the directrix at y equals minus C. We'll call this the parabola in standard position. And it has this wonderful equation. If you put it like that, x squared equals 4cy. And then you can translate it around the plane by replacing x by x minus x0 and y by y minus y0. Put this vertex anywhere you want. But the coordinates of the vertex are always the translation, right? Because it's at 0, 0 if you put it in standard position there. All right. So we can also do a short problem like that. I guess I should mention their properties too. Maybe you've seen this before. You ever seen a Newtonian telescope named after Isaac Newton? And his idea was this terrible problem. People used lenses to refract light. The light would come through the front lens and it'd be bent back here. And then they'd take a little lens down here and focus on the image, and the ratio of this distance to this distance was the power of the telescope. But the light gathering power, how big this front lens was, determined how much you could see, really, because you needed to gather a lot of light to be able to see tiny things, faint things. And so it was important this was big, but that meant the whole thing was really heavy because you had a big piece of glass up here that was way out in the telescope. But on top of that, the bigger problem was that when it refracted light, different colors refracted differently. So maybe this is the blue light, and then the red light would be bent a little differently, and it would focus at different points. So your colors would be all blurry, right? It wouldn't focus quite right on all the colors at once. So Isaac Newton came up with this idea. Why not make a telescope tube like this and make a curved surface here, and light will come down off this surface and focus off the mirror to a point. And we mentioned this telescope last time. You put a little diagonal mirror here, flat mirror, to reflect it so it actually focuses over here. Then you can take a eyepiece out here and focus on this image. It has the same result. The power is the ratio of this focal length to this focal length. But now there's no chromatic aberration, they call it, no color distortion, because it's a reflection, not a refraction. It just bounces off the mirror. It doesn't get bent through glass. And so that was Newton's telescope, and you can see why it would be popular. And what curve is this, though, that would focus light to a point? Turns out to be a parabola. So this is actually fundamental in solar collectors, right? You try and make objects hot. You also use a parabola, or you see these radar dishes. Radar is just electromagnetic radiation like light. It's just a frequency you can't see. It will collect, radio waves and focus them to a point, kind of thing. And flashlights work that way, right? You have a flashlight with a bulb, and the center circle from the flashlight is the beam, and then you have that's reflected off the mirrored surface and back. Ideally, you have a parabola back here, although they're sloppy on cheap flashlights, of course. But then the light coming out the side makes the big circle on the wall. So you get a little circle from what's bouncing off the parabola going the other direction. Coming from a point goes into parallel light rays. Anyway, so parabolas have all sorts of applications like that. And this standard equation. So now let's see if we can do a parabola here. Example. Find the parabola given that its vertex is y equals minus 6. I'm sorry, its vertex is 0, 1, and its directrix is y equals minus 6. 0, 1, directrix. I'm going to change that, y equals minus 7. All right? So suppose that's what we know about it geometrically. Another problem, they might give you the focus on the directrix or something like that. What can we do with that now? Well, first you want to see if it's opening up and down or left and right, right? Our standard one is for a parabola opening up, right? It was x squared equals 4cy. With c positive, if c is negative, you can make it open down actually. But if you replace it, so this is vertical with c positive or negative to go up or down, vertical. If you want to make it horizontal, you just interchange x and y, and you're like y squared equals 4cx, right? Then you can translate it by replacing x by x minus x0 and y by y minus y0 and get translated equations. This one, if this is the vertex and this is the directrix, I know the distance from the vertex to the directrix is c. It goes from y equals 1 to y equals minus 7, so c is 1 minus a negative 7 is 8, right? The distance perpendicular from the vertex to the directrix. Now I've got it because if the directrix is y equals minus 7, sometimes it helps to just draw this in your mind, and the vertex is 0, 1, then we know it's a parabola opening up, through the vertex. Started to draw that as the focus. Opening up like this, going through the vertex. And evidently this is 8. So it's 8 more units up to the focus, the focus must be at 0, 9, right? Because these distances are the same. All right, so now there's the focus. And you can write the equation immediately, right? This is a standard position, just shifted so the vertex is 1 unit up. So we take and first write down from the standard, x squared equals 4cy. We're going to translate it up 1 unit and make it replace y by y minus 1. X squared equals 4cy minus 1. Moves the vertex up 1 unit. And then c is equal to 8 by noting the distance from the vertex to the directrix. With c equals 8, we get x squared equals 32 times y minus 1. There's the equation, or if you put it 4 times 8, we'll say that's in standard form. But you can multiply that out and get a y equals ax squared plus bx plus c, right? So the standard form for the parabola, then you can multiply out to get an equation y equals ax squared plus bx plus c that you've gotten know and love from algebra as the equation for a general vertical parabola. Okay. Boy, it just seems like our time goes by so fast here. I want to mention one more thing here. We have a little more time next time if we need it, but here's an even more interesting thing. I alluded to this last time. This is a note that the book puts in there, and they don't do a good job with it now because they're going to do it later. What's the simplest equations you have in mathematics in 2 variables, right? They're linear equations, right? Ax plus by, in the plane, it's ax plus by equals c. Here's a linear equation in 2 variables, a general linear equation. If a and b aren't both 0, we call it a linear equation in 2 variables. What's the next simplest equation? Well, maybe with squares. Ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. So it's like that one, just with squared terms and this cross term. That's the second power equation, sort of the next simplest thing you want to think about in algebra. Can you imagine what kind of curves you get out of this? It's always either a conic section that turns out, one of these curves we just did, to a degenerate case, such as a pair of intersecting lines or a point or something like that. Or, I don't usually include it in the degenerate cases, no solution is possible, right? You can put all these letters but f equal to 0 and you get 2 equals 0 or something and there's no solution. Isn't that fascinating? Every second order polynomial equation in 2 variables equal to 0. Every second order polynomial equation in 2 variables is a conic section, degenerate case, or no solution. So in some sense, these are the simplest things after lines. They come up a lot in nature and all sorts of other things. How do you tell which one it is? Here's the hint. I think I'm out of time. Yep. If a conic section, then you can figure out which one it is. B squared minus 4ac bigger than 0 is a hyperbola. B squared minus 4ac equals 0 is a parabola. And b squared minus 4ac less than 0 is an ellipse or a circle. And it's like the orbits we drew, right? The higher energy has the higher b squared minus 4ac. So if the hyperbolas had the most energy, the positive ones, and these are... Anyway, so you can look at an equation like this. 4x squared plus 5xy plus 6y squared equals 24. What is that? If it's a conic section, if you know it's a conic section, it's a... Well, here's A, B, and C, and you say b squared minus 4ac, just to do this quickly. The discriminant you knew from algebra is 5 squared minus 4 times 6 is negative. So it must be an ellipse, right? This is less than 0. All right. The only thing is these equations generally have to be a rotated thing. We haven't talked how to rotate these. That's why the book doesn't do more with them yet. Thank you for coming in today.